Alright, so we've been analyzing this equation. We have acetic acid reacting with sodium bicarbonate. So, acetic acid is written weird. This is the anion. This is the cation. Normally we write it as the cation first, with the anion here. This is a double displacement reaction. So the cation is going to make a react with the anion here. To make sodium acetate. And the cation here, H, is going to react with the anion here. When these react together, it does these hydrogens group together to make this covalent ionic. Actually, it makes it an acid. This is carbonic acid. And carbonic acid is unstable. It's in the presence of water, it's constantly converting itself between CO2 and water. This is balanced. And thus, we can replace this portion right here in the equation. But this is double displacement. Does anyone know what glucose, sucrose, and fructose are? All versions of sugar. Do y'all know the difference? So when you get to very complicated organic structures, this is where we end up. It becomes problematic to reference something by just a formula. Glucose and fructose are two different chemicals. So here is any every intersection is a carbon. Here's the structure of glucose. Its formula is C6H12O6. And here is fructose. Its formula is the exact same as glucose, but you might notice it's rearranged slightly differently. The hydrogens are bonded in different locations, making it a very similar chemical, but not exactly. Here is probably the notation y'all are more used to. Which brings us to sucrose. What is sucrose? Sucrose is table sugar. That's the sugar you actually use in the kitchen. Glucose is the sugar that is actually useful for chemistry. It's your blood sugar. It's the sugar your body converts sucrose into. And sucrose is actually a combination of glucose and fructose bonded together. So if you take a glucose, which is C6H12O6, and you take a fructose, which is also C6H12O6. And you combine them together so that they share one oxygen. You get sucrose, which is C12, and let me make sure. C12, and they share more than one oxygen. H22 and O11. They share some hydrogen too. So I think they share one H2O molecule. You can see sucrose right here, bonded. So we have, this would be glucose, that would be sucrose portion. I want to analyze one more complicated thing that I plan on doing. It's called the gummy bear reaction. Much more cooler experiment. It involves a reaction of sucrose with potassium, potassium chlorate. So let's analyze this reaction. We have C12, H22, O11, and we're going to react it with, what's the formula for potassium chlorate? Yeah, potassium in it. What's the chlorate ion? So the 8 tells you it's an oxyion, ClO3, and it's a 1-to-1. This is a negative, that's a positive, so it's 1-to-1. And what does this reaction give us? Is this ionic? Is sugar ionic? No, so we can't use our ionic rules. So let's use the rules we've already known. Let's look at our only ionic formula in this whole thing. Potassium chlorate. What do you think is something we can do with it by itself? What is something we can make it react by itself with? Or not really with, but what's one of the things? So what all types of reactions do we have? We have synthesis, decomposition. So what would it decompose into? So chlorate is an ion. Ions don't exist by themselves. So we have to make it decompose into two compounds. They have to be compounds, key thing. What is two possibilities for these compounds? So, and just use common things you're used to. So, you're used to carbon monoxide. However, so this is an ion. Is this an ion? Or a compound? Unlikely. Remember, chlorine and oxygen are very electronegative. They don't really like to stay bonded with each other unless they're bonded to something else. Any combination of C, L, and O are usually not going to be compounds. What is something else you are used to? What's a molecule you are used to that has calcium, chlorine, and oxygen? Just oxygen. O2. And you are used to table salt, right? NaCl.
I was going to say potassium chloride, but I didn't think there would be an oxygen like that.
So potassium chloride is a very common ionic compound. It's a salt substitute. It's very similar to regular table salt. Has very similar properties. There's not much difference between them. They actually use it as a substitute for salt. And what's left over is oxygen. Of course, we have to balance the equation. So, what would be the prescripts, subscripts? Two, 2, and 3. So, potassium chlorate, not ite, can decompose into sodium chloride and oxygen. So the reason their intuition should be, you should see potassium chloride and that should immediately scream to you the ionic compound KCl. This is a very common ionic compound. If you see NaCl in some chemical, that should immediately scream to you it's going to make salt. If you can get an ionic compound from this, another ionic compound, that's usually going to be, and wherever's left over, you can work with that. But this is how it decomposes. We'll get to how we make it decompose in a little bit. And let's look at another reaction. So, sucrose is not very useful by itself. But I just told you that it has glucose and fructose in it. Glucose is very useful in science. And it's not exactly what we're used to, as there's something additional to it. What do you think this type of reaction is going to be? So we have decomposition. I can tell you it's not decomposition though. We can have synthesis, but it doesn't really look like anything synthesis. What's another thing we could do with it?
We would just go to carbon dioxide and water.
Combustion. You are right. So we're going to mix with oxygen. Luckily, we've made some right here by decomposing that. And you're right, the products of a combustion reaction is CO2 with water. So what's the balanced version of this? So to get the hydrogen to match, what do we need to add over here? So there's only one hydrogen here and one hydrogen here. That means that I know it's going to be a 6-to-1 ratio. So whatever the subscript here is, I need 6 times as many water as it. Let's see if 6 will work. If not, we'll try 2 and 12, or 3 and 18, and so forth. How many carbon do we have? Well, there's only 1 carbon on this side, 1 carbon here. I know the ratio is 1 to 6. Or 1 of these molecules to 6 of these. So wherever this subscript is, I'm going to need 6 times that and 6 times that. Let's see if we can now somewhat balance this. So I have 6 carbon, I have 12 hydrogen. How many oxygen do I have? So carbon is 6 and 6. Hydrogen is 12 and 12. And oxygen on the left is how many currently? 8. 6 plus 2. And on the right, it is 6 times 2, that's 12, plus 6, which is 18. So I need to add exactly... Wait, is that right? 6 times that is 12, plus that. 6 and 8. Yeah. Wait. Yeah. So I need... Be better to write this as 6 plus 2. That's what's been messing up in my head. So I need... Luckily, the only thing that's missing is, or unbalanced, is the oxygen. So I need 6 plus 2 times x. So here's my x. What do I need to make x to make the 18 in this? So I have 6 plus 2 times x is equal to 18.
So we need 6.
I need 6. So that's the balance equation for this equation. So I know combustion of glucose equation, and I know how to decompose potassium chlorate, or at least I know the equation part. The overall reaction combining these two is we have sucrose, which is a solid. It's not ionic. We have potassium chlorate. It's ionic, so does it dissolve in water? And I should say this, aqueous means dissolves to form ions in water. Not just dissolves, it means disassociates into ions. The sugar, even though sugar dissolves in water, is not aqueous because it stays a sugar. This is going to, if it is aqueous, break up into K plus and ClO3 ions. So is this aqueous? Do you have your solubility thing? Your solubility rules are going to be very useful here on out, by the way.
I don't know anything about fluids.
As always, in chemistry, there are so many exceptions, and you gotta guesstimate often. So all chlorides are soluble all salts of potassium are, except several. So this is not a common rule of one. Well, if it doesn't meet any common rules, Google. Solubility. It's soluble in glycerol, negligible in acetone and liquid. Soluble in water is barely anything. But it doesn't really matter in this equation because we're definitely not using any water. Water is not involved in here. Looking at my overall cheat sheet for this thing, which I just closed. They put it as a solid, but it's not a solid. Technically, it'll be a liquid. But it doesn't really matter. They put solid. So, we're going to get some KCl combining these. Some oxygen. No, we're not. Let me see. Make sure I'm doing this right. We're basically making an explosive, by the way. So oxygen is an intermediate. So this oxygen is being consumed right here. So it doesn't exist on the right-hand side of the equation. We get CO2 and we get H2O. Which would be a gas, and this is a liquid, and this is a solid. So, analyzing the equation like this, basically we take some assumptions. What can we possibly do to this? We know that we can decompose this chemical. Glucose is a very, very common reaction. It's used in biology. Everything uses glucose. This is something most people have memorized. And thus, if you have a chemical like this that contains glucose, oftentimes you can just substitute this into it and assume that this will break the glucose off. And we assume any other things are going to be a combination of CO2 and H2O. Does that make sense, kind of? Basically, I'm breaking off a glucose from this to do this reaction. And and part of the fructose is going to decompose into H2O and CO2. That's just how, because that's the only chemicals you can really get from C, H, and O. Thus, the overall reaction is C12H22O plus, and what will be the balanced form of this? I wrote it as this. So what will be the subscripts? So it's very good to find 1-in-1 ratios. So find them. So if there's only one molecule on the left that contains something and one molecule on the right that contains something, start there. So carbon, for example. Carbon only appears once on the left and once on the right. We see 12 carbon here and 12 carbon here, or 1 carbon here. So I know the ratio is going to be 1 molecule of this for every 12 molecules of this. I could be wrong. It could be 2 and 24, or 3 and 36, or so forth. But usually it stays low. What else? The next thing I would do is try to balance the oxygen. Oh, no, hydrogen. So, hydrogen, I'm going to assume one of these. So this is going to be a 11 to 1 ratio. So 11 times 2 gives you 22. Next, balance the oxygen, because there's oxygen in this. This is already balanced. The potassium and chlorine are already balanced right now, temporarily. So we have 11 plus 3 times x on this side. And that has to equal 24 plus 11. So that's 35, right? So what must x be? So that's 3x. That'd be 24. What is 24 divided by 3? 8. And I just need to double this by 8. Alright. What are ways... Next thing to do is, how can we decompose potassium chlorate? What do y'all think? How can we do you think we can make it just decompose on its own? Should be obvious. That would be dissociate, where it breaks apart into ions, not decompose. What do you think most things decompose? The reason why. There are exceptions, but most things. So most elements are held together by chemical bonds, and how can you break those chemical bonds? So the reason why they're stuck together is because they have chemical bonds forcing them together. And those chemical bonds are strong. How in the world can you break those chemical bonds? By not using another chemical. By just making it break it by itself. So remember when we have molecules, so let's look at water. How can we make water decompose? Well, we know that this hydrogen and this oxygen are vibrating back and forth. They are vibrating to the side. If you remember when we went in, and that's how microwaves work. And temperature is how much they're vibrating. What if I heated this up? What if I placed some water in the sun? It would not evaporate. It would decompose quite quickly. This hydrogen would be vibrating so much, it would vibrate away from the oxygen. It would not be a molecule. It would be a C of H plus and O2 negative ions. Temperature is how you make things decompose. You heat a chemical up to a hot enough temperature, it does no longer stay as a chemical. It breaks apart into atoms or ions. If it breaks down to ions, that's called a plasma. Plasma is when it gets to a hot enough temperature that it stays as ions. And the sun is so hot that it actually breaks compounds down, ions down into their actual individual atoms. So, basically, melt KClO3 and drop sugar in it. we melt KlCl3, it will slowly start decomposing. We need high temperature for it to fully decompose. But when we... Now let's look at something else. Let's go back to the vinegar reaction. Is this a redox reaction? What's the charge of this ion? -1. Charge of this one, or I should say oxidation number, +1. What is the oxidation number of these hydrogens over here? Still +1. What is the hydrogen right in here? +1. What is the sodium? Oxidation number? +1. What's the sodium over here? And what is this whole ion? -1. We know nothing inside this ion has changed because it's still -1. And we can do the same thing for this carbon and that. Nothing inside this has changed. So did any oxidation numbers change from left side to right side? So this is not redox. And what I tell you about redox reactions, what is something special about them? What do they do? They change the oxidation number, that's the definition of redox, but what do they release? Energy, heat. And was it you, Lucas, that asked if it got hot? Did it get hot? It stayed the same temperature. Even though you saw the violent bubbling of the vinegar in the reaction we did yesterday, no heat was produced. This is not a redox reaction. Let's analyze this one. What is the Cl? So let's look. We have potassium chlorate. What is the oxidation number of the chlorine? So what is the rule? Oxygen is always -2. Group 1 is always +1. And this is a neutral compound, so the charge of it, the sum has to equal 0. So we have +1 plus whatever chlorine is, plus 3 times -2, and that has to equal 0. So what is chlorine? So -6 and +1, they combine to be +5. Moving it over here. And that should be -5. We see chlorine is +5. Now let's look at it over here. Potassium chloride. This is an ionic compound. In ionic compounds, whatever their charge is the same as their oxidation number. So this breaks up into K plus and Cl negative. That means this is +1 and this is -1. So is chlorine being oxidized or reduced? It's being reduced. It's our oxidizing agent. Thus, what is also being produced here? Heat. And what does heat do? Heat leads to the decomposition of potassium chlorate. Potassium chlorate supplies oxygen to the glucose portion of sucrose, which then does this reaction, which then produces more heat. More heat comes and decomposes more potassium chlorate. Potassium chlorate produces oxygen that can react with the glucose portion because it's a loose bond of the sucrose, which thus produces more heat. And what do we get? We get a runaway condition of rapid production of heat. That's literally the definition of an explosion. An explosion requires an oxidation reaction. So let's look up what this is going to look like. I didn't search for good videos. Let's see if this one is good. So, molten potassium chlorate. Very, very dangerous. No, what are you doing?
Oh no.
Do you see the heat being produced? And the giant stream of fire?
Oh, that poor bear. That's satisfying.
Now, what he just did was very stupid. Because you saw, as soon as it touched, it immediately shot a flame out. And where was his fingers? He got out in like less than a half a second.
Oh, God.
By the way, this experiment is going to be quite dangerous. As what's the difference between a burn and an explosion? A explosion requires a contained container that can build up pressure and thus release all of its energy at once. Actually, let me just Google that, as this guy released a good one. Low explosion versus high explosion. Was it Tom? Yeah, Tom Scott. British guy.
Have you ever realised that all your life you've missed something that's kind of obvious? It doesn't have to be something important, it might just be really minor, but maybe someone says a word and your brain just kind of shifts a little as you realise that you've never thought of that, and it sort of feels like you should have. Last time I was making a video here at this explosives test facility, I just casually used the phrase high explosives because I think I assumed that high explosive just meant really, really explosive. So I was surprised when Steve, the explosives expert, pointed out that it is a technical term, and there is also low explosive. So the obvious thing to do was to demonstrate both.
We will be making
are a mixture of a fuel and an oxidizer. With low explosives, these are roughly mixed together, so they're particles of the two in close proximity. When a low explosive reacts, it's a thermal reaction, so it's heat travelling through the low explosive, causing the chemical reaction to occur. As it burns, the fuel and the oxidizer react together, producing lots of gas. That will just bleed off into the atmosphere as a big puff of smoke.
So this is not an explosion. This is low explosive. This is gunpowder. And it almost meets the definition of explosion, a sudden release of gas due to oxidizing agent reacting.
In order to make
I
a
wouldn't really classify that as an explosion, though.
low explosive have a more violent reaction, you need to contain it. So you need to hold those gases in and allow the gas pressure to build up until it bursts through the container that you've put it in. So you've got deflagration. It's just when you hold all the material in and the gas pressure, so the pressure builds up, which creates more heat, which makes the low explosive react even faster. It's a runaway reaction, And eventually, the amount of gas produced overcomes the container it's in and bursts it open, making a bang.
So a low explosive, just like any other fuel, is a thing that burns. It just burns quickly. The gas that it releases expands and builds up pressure, and then...
That's an explosion. So the thing we'll be doing is hopefully burning, not exploding. But you're putting a gummy bear down the end of a tube that can block the tube, while a portion of it is reacting at the bottom. The gases have to travel around the gummy bear to get out. But there's a chance that it sticks to the side and creates a sealed loop. The pressure suddenly builds up and you have exploding glass all over your face. Goggles and apron. It shouldn't explode. But if it does, I just need to stand back. Shouldn't be any major things as it is not completely sealed. I think you're curious about how high
it's also a mixture of a fuel and oxidizer. But it's not actually a mixture. It's down on the molecular level. So you've actually got the atoms of material in such close proximity that they're linked together within the molecule. And because they're so close together, they can react a whole lot faster. So rather than it being a thermal reaction that propagates through, it's actually a shockwave reaction. It's so fast that the shockwave can cause the chemical reaction to occur. The chemical reaction produces energy, which then sustains the shockwave, driving it on even faster. And that's why high explosives can actually go off at between 6 to 9,000 meters per second, which is pretty damn fast.
Sometimes.
Because high explosives require a shockwave to detonate properly, they can be exposed to heat and flame and will normally just burn away. In fact, you're actually allowed to have...
Okay, so I want you to note how close he is. Y'all see how close he was to this high explosive?
50 kilos of high explosive in your car without having to put a hazard symbol up on your
He's
vehicle.
burning it like a candle.
It's considered not to be that big a...
You can take C4 and use it as candle wax. I wouldn't recommend it. It produces cyanide and stuff. Dangerous chemicals, toxins.
problem. Obviously, when the fire brigade see you pinned behind the steering wheel on your car at the side of the road and it's on fire, they're going to stand back and sell tickets rather than actually fighting the fire. So what you use is a detonator to give it a shockwave to get it going. A detonator itself is a little metal tube. Inside there's a small amount of secondary high explosive, a tiny amount of primary explosive, which is set off very easily, and then there's some sort of initiation system that will then set off that primary explosive. With electrical detonators, that's an electrical fuse head, and you pass a current through the fuse head. That produces a flash as it burns out. That sets off your primary explosive, which supplies a shockwave into your small amount of secondary explosive, which amplifies the effect. That then bigger shockwave then transfers into your main charge, which is then sufficient to set off the main block of explosive.
Which means, weirdly, that high explosives can be safer than low explosives, despite the name. If there's an accident around a load of low explosives, they're all going to catch fire and go up. But around high explosives, as long as you keep the primaries separate, like you're supposed to, it takes a lot to make a high explosive detonate, or sometimes even to burn. That is, until you want them to.
Stand by for firing.
Now then, out of all these, burning the gunpowder, making the pipe bomb and gunpowder, burning the Semtex, but actually when he detonates the Semtex, a high explosive, notice the distance. Low explosives, if you have a large amount, is dangerous. But even if that explodes, my concern is not the exploding glass. Even though it will cut your face, as long as you got goggles on, it's just a scratch. And it shouldn't really even break skin. I honestly think if that exploded in your face, it's very unlikely that you would get a scratch. And if you did get a scratch, it'd be superficial. My concern is only the exploding reaction liquid that's burning and catching fire, sticking to you, especially the fact that it's sugar. But if you're far enough away, it shouldn't be that dangerous anyway. I'll also probably do it in the fume hood anyway, which you have a barrier plexiglass there too.
Firing now.
Oh, and also, because of how quickly the reaction goes off, any small bit of debris could be flying at tremendous speeds. But Gummy reaction. That's what I'm hoping too, to get the purple. The one on the left has a lot of carbon in it. It's not burning as cleanly. The orange glow is from carbon in it. So we might have to go outside for this. Because our fume hood doesn't work. It doesn't blow, and I bet you that it's going to produce a lot of smoke. It looks like they're doing it in a high school chemistry lab, and fire alarms aren't going off. And doesn't that look like it? So, our reaction is supposed to be, theoretically, again, real world is different from theoretics. It's supposed to be carbon, salt, and water. None of those are supposed to smell, but I have a feeling we're going to get also burnt sugar going up in the air too. That does have most definitely a smell and will set off the fire alarms. And carbon too. I have checked that our gas works. Oh yeah. So he's getting it to start decomposing. So when heated, potassium chloride decomposes into potassium chloride. But right now it's at such a low temperature, it's slow. I forgot, this is the symbol for decomposition. It's the Greek letter D, delta.